everyone, welcome to part 4 of the chapter 10 lecture. This will be on intermolecular forces. So make sure you've done, all of the practice problems leading up to this, all of the homeworks leading up to this, because we are going to use all of the other portions from chapter 10 that we've learned so far to learn about intermolecular forces. So, intermolecular forces are attractive forces. And they are, so there's two different types. We have intramolecular forces, which are bonding forces. So these are forces that we've learned about so far. So this is things like ionic bonds and covalent bonds. These forces act within each molecule. So this is not going to be the focus of our lecture. I just want to draw your attention to the fact that this is intramolecular forces. But these intramolecular forces, these bonding forces, right, are influencing the chemical properties of the substance. So ionic compounds are different, right? They're solids at room temperature. They have really high melting points, high boiling points. They influence those physical properties, and they also influence the chemical properties of the substance, how the molecules react, okay? Intermolecular forces is going to be the focus of today's lecture. And so these are going to be non-bonding forces. These are forces between molecules. So this is like how a water molecule interacts with another water molecule. And so these will be influencing physical properties of the substance. So if things have really strong intermolecular forces, like ionic compounds have really strong intermolecular forces, they'll have really high melting points, high boiling points. If things have really weak intermolecular forces, like nonpolar molecules, then they will have really low melting points. And these are things that typically exist as like gases at room temperature and things like that. So the focus of today's lecture is going to be on intermolecular forces, the forces between two different molecules. Okay, so attractive forces between molecules and ions hold them together in liquids and solids. So things that have stronger intermolecular forces are more likely to be solids at room temperature, or maybe if they're a little weaker, then it might be a liquid at room temperature. Substances that have really weak intermolecular forces will likely be a gas at room temperature. And so the way that we change phase, right? We go from a solid to a liquid or a liquid to a gas. We have to break these intermolecular forces, these intermolecular attractions. And the stronger those attractions are, the higher the melting point, the higher the boiling point. The more energy you're going to have to put in order to break those attractions. Okay? So there are 3 types of intermolecular forces that we're going to look at in this class. There are others, but again, this is an introduction to chemistry, so we're going to start with a couple. So these ones are going to be dipole-dipole attractions, hydrogen bonding, and dispersion forces, which you'll also hear me call London dispersion forces, or London forces. Okay, so these, this is the same thing. Okay. So the strongest forces are going to be ionic bonds. Those are the strongest things that are holding our molecules together because they have that complete transfer of electrons. We have complete positive charges, complete negative charges. Those form really strong attractions between the molecules. So that would be the strongest. And then covalent bonds are going to be followed right after that. But these 2 types of forces, these are intermolecular forces. And we are going to look at intramolecular forces. So for our intramolecular forces, the strongest one that we are going to talk about is hydrogen bonding. And then our next one will be dipole-dipole interactions. And our weakest one will be the London dispersion forces. So these 3 are the ones that we are focusing on today. These are intramolecular forces. Oops, sorry. Oh, wow, okay. Inter. Ooh, goodness. Sorry, guys. A lot going on. All right. Intramolecular forces versus intermolecular forces. Sorry, I didn't mean to confuse you all there. goodness. Okay, hang on. Got me all flustered. All right. Intermolecular forces is what we are focusing on today. Sorry, had that all backwards. My apologies if I'm confusing you there. These are intramolecular forces. The other ones are intermolecular forces. Sorry about that. Hydrogen bonding, intermolecular force, not inter. And so this is an attraction, not a bond. So I want to be very, very clear with that because the name is hydrogen bonding. And it's a very bad name because it's an attraction, not a bond. So make sure you know that. It's between a hydrogen and very electronegative neighboring atoms. So oxygen, nitrogen, and fluorine. So the way that you're going to remember this, I have lots of corny, cheesy chemistry jokes. You're going to remember that hydrogen bonds just want to have fun, right? Sorry about that. But they do. They want to have fun. So they want to bond to fluorine, oxygen, or nitrogen. So the way a hydrogen bond will happen is we need to have a hydrogen bonded to an oxygen and attracted to a nitrogen. Okay, it needs to be bonded to one of the FON atoms and attracted to another FON atom. They can be the same one or they can be different ones, but so here, hydrogen bonded to an oxygen, which shows up in FON, and attracted to the nitrogen, which also shows up in FON. Okay, so this attraction here, that is the hydrogen bond. So it's between two molecules, not this one within it, right? The one from hydrogen to oxygen, that's just a covalent bond. It's a polar covalent bond. But the attraction here from that hydrogen to the nitrogen, not a bond, but an attraction between two molecules, that is what's called the hydrogen bond. Okay, so this is the hydrogen bonding between ammonia, which is NH3, and water, right, which we all know. Okay, so that's hydrogen bonding. So hydrogen bond occurs between polar molecules that contain hydrogen atoms that are bonded to really electronegative atoms. So fluorine, nitrogen, oxygen. Again, we're looking for hydrogen bonds, just want to have fun. So a hydrogen atom, and so the reason this happens is that when a hydrogen atom is bonded to a really electronegative atom, so like nitrogen, oxygen, fluorine, right? We get a big separation of charge. This is a big delta minus, a big delta positive. So this hydrogen is really electropositive, and this nitrogen is really electronegative, okay? And so this, because we have, kind of a big positive, big negative, that is a very strong attraction. But again, I know it's called hydrogen bond. It is not a bond. It is an attraction. Okay, same thing's happening on the right. We have a hydrogen bonded to a really electronegative atom and attracted to another really electronegative atom. So the hydrogen bond part is the attraction, not a bond. So here's another one, right? This is a little bit more complex. This is a chemical called methanol. And we have a hydrogen here, which is bonded to a really electronegative atom, right? Again, we're looking for FON. So it's bonded to an oxygen and attracted to another really electronegative atom. So this attraction here, that is the hydrogen bond. Okay, and so the way that you'll be able to recognize this in a molecule is if a molecule has HF, OH, or NH, right? So a hydrogen bonded to one of these, right? HF, OH, or NH, right? Hydrogen bonded to any of those. Those will have hydrogen bonding, and these are really strong intermolecular forces. So they have really high melting and boiling points for their size. Normally, molecules, we can kind of look at them and see based on their molecular weight or their molar mass, right? Whether they might be a solid or a liquid or a gas at room temperature. But these molecules, even though they're small and they have low molecular weights, they'll be, they're more likely to be liquids or solids at room temperature because they have these really strong intermolecular forces. So like these methanol molecules are holding on really strongly to the other methanol molecules, and this is a liquid at room temperature. Okay, so they have unusually high melting and boiling points. And again, this kind of attraction is called a hydrogen bond. It is an attraction, not a bond. Our other type, so that's like the trickiest type of intermolecular force to recognize. The other two are more straightforward. So one of them is dipole-dipole attractions, and this will happen for polar molecules. Okay, so if your molecule is polar, then it will have dipole-dipole forces. It may also have hydrogen bonding, but it will always have dipole-dipole forces if it's polar. So again, you need to be able to recognize, is your molecule polar or nonpolar, which is what we talked about in that last set of slides. So polar molecules are attracted to each other by dipole-dipole attractions. And so this dipole-dipole attraction happens when the positive end of one dipole, like this, is attracted to the negative end of another dipole. Okay, so the positive part of one polar molecule is attracted to the negative part of the other molecule, right? Because we know positives and negatives attract. And so this attraction here, that's the dipole-dipole attraction. So dipole-dipole forces. And this will happen between any polar molecule. They'll orient themselves, they'll arrange themselves so that the positive part of one molecule is near the negative part of another molecule. And again, these aren't complete positives, complete negatives, right? These partial positives, partial negatives that we talked about last time. So if we look, these are different molecules. So this, the one on the far left, that's propane. That is a nonpolar molecule, and it has a very low melting point, a boiling point, because it's not very polar. So this dipole moment that it's talking about is how polar your molecule is. So you can kind of tell based on the coloring here in the pictures. The more red, like dark red and dark blue you see, that is telling you how things are polar, how they're polarized. The red is really electronegative. So like here, this is like the delta minus side. This would be the delta plus side. And it's just how we talk about things as chemists. So as we get more and more and more polar, right? So this blue, right, as the blue, the blue parts of this graph, as we get more and more and more polar, a larger and larger and larger dipole moment, you can see, based on the orange bars, that the boiling point is going up in general. Okay, so as things get more polar, they are going to have larger and larger and larger dipole moments, which means they will have larger and larger and larger boiling points because there's more of these dipole-dipole interactions. Our last type of intermolecular force is London dispersion forces, or sometimes, like I said, just called dispersion forces. This is for nonpolar molecules. Okay, so this is, if you see that your molecule is nonpolar, it has London dispersion forces, that's it, the end. No more thinking that has to go into it. It's just if it's nonpolar, London dispersion forces hold it together, hold it between other molecules. I'm going to spend some time, though, explaining what London dispersion forces are, because I think it's fairly easy to understand what, dipole-dipole attractions are. The negative side of one molecule is attracted to the positive side of the other because negatives and positives attract. It's a little bit trickier to talk about London dispersion forces. London dispersion forces are the temporary separations of charge that happens in a molecule. So a couple things I want you to know. The London forces increase with the size of the molecule. So as the molecule gets bigger, it has larger and larger and larger London dispersion forces. Okay, and this is because there are more electrons in that molecule, and so there are more electrons that can be polarized. And I'm going to show you what London dispersion forces mean. But just in general, as a trend, as your molecule gets bigger, you get more and more and more London dispersion forces because there are more electrons. So I'll show you what I mean. So dispersion forces, these are weak attractive forces. Remember, hydrogen bonding is going to be our strongest intermolecular force. And then dipole-dipole is going to be below that. London dispersion forces are like way below that. They're super weak attractive forces. And they happen again between nonpolar molecules. And this happens when the movement of electrons induces a temporary distortion. Okay, creates a temporary dipole. So if we look, and I know that doesn't make a lot of sense right now, but if we look at this, this helium here, in frame 1, the electrons are kind of, one's on one side, one's on the other. Frame 2, one's on one side, one's on the other. But you see in frame 3 here, the electrons have ended up on the same side. And this just happens randomly. The electrons are just kind of zooming all around, and every once in a while, they'll both end up on the same side. Well, when they end up on the same side, that makes this side of the molecule partially negative. Of the atom, sorry. And this side of the atom, partially positive. Right? Because one side, right, this side has more electrons than it really should. If we were thinking about maybe one electron usually sits on each side. But now there's 2, right? So that side is partially negative and this side is partially positive. So now instead of our atom being, uniform throughout, one side of it has a partial negative and one side of it has a partial positive. Well, let's take that atom and say, okay, now it's here. So the electrons are both on the same side. Well, if it came near another helium atom, like this one, well, if this side is partially positive, then the electrons in this atom are attracted to that partial positive. So now they go hang out on this side of the molecule to be near the partial positive, which makes this side of the atom partially negative because the electrons are on that side. And that made this side of the atom partially positive because now there's no electrons on that side. So then if it comes into contact with another helium atom, well, these electrons now are attracted to the partial positive, and so they hang out on the left side of the atom, which makes this side partially negative, and then that makes this partially positive. We call that an induced dipole, where this one had just, a dipole that happened to happen, and it came near another helium atom and it caused a dipole. It induced a dipole. It caused these electrons to hang out on one side of the atom, which made it partially negative and the other side partially positive. And so these are temporary dipoles. They happen for like, a millisecond, a second. This very, very fast. And so this temporary dipole makes it possible, though, for some nonpolar molecules to exist as liquids and solids. Otherwise, all nonpolar molecules would just exist as a gas because they don't have any way of being attracted to each other. Like the polar molecules, right? We have the partial positives are attracted to the partial negatives, and so they can form really strong attractions. But nonpolar molecules don't have that. They're nonpolar. The electrons just kind of hang out equally dispersed. So the only way these nonpolar molecules can be attracted to other nonpolar molecules is this temporary dipole. I have more pictures. So let's look at atom A and B up here, like section 1. The electrons are just kind of hanging out, evenly dispersed throughout the atom, right? We've got that, positive nucleus in the middle. And let's say there's an instantaneous dipole that happens on atom A, right? At some point, all of the electrons or more of the electrons end up on one side than the other. Just because electrons, right, they're zooming around, they're doing their own thing, and at any given point, some of them might be more on one side than the other. Well, when there's more electrons on the left here, this side now is partially negative, and this side now is partially positive. We call that an instantaneous dipole. It just kind of happens. But when it happens, now the electrons in atom B are seeing this side is partially positive. Well, the negative electrons in atom B are attracted to that partial positive, so they will shift themselves this way in the atom so that they can be closer to that partial positive. So now we see this happen. The electrons in atom B have shifted themselves closer to atom A so that they can be near that partial positive. This is what's called an induced dipole. So the instantaneous dipole is on atom A, just kind of happened, and the induced dipole happens on atom B because of atom A. So again, now we have an attraction here, right? The partial positive is attracted to the partial negative, and so that is the London dispersion force. Okay, here's another picture. Same kind of thing, just now we're showing with different colors. So here's, in the first bit, molecule A and B, nothing's happening. And so, if we go here, now an instantaneous dipole happens on molecule A. More electrons are hanging out on the left side than there are on the right side. And when that happens, that causes this side to be partial negative, this side to be partial positive, and when the right side is partial positive, the electrons in molecule B are like, hey, we're attracted to the partial positive, let's hang out on the left side of the molecule. And so then we get an induced dipole on molecule B, and now it can experience London dispersion forces between that partial positive and partial negative. So I know that this is a little bit tricky to understand, these London dispersion forces. But again, you'll recognize when they happen at the very least. These are always nonpolar molecules that can do this. Okay, so if you see nonpolar molecules, London dispersion forces. So here is a summary of all of our different types of forces. So the ionic bonds and covalent bonds, these are going to be within an atom. These are, and I'll get my thing right here, intramolecular forces, okay, which again, not the focus of today, but these are very, very, very strong. These are what happen within a molecule. Between the molecules, though, hydrogen bonds are going to be our strongest between the molecules. And you're going to remember hydrogen bonds, right? They want to have fun. Okay, so a hydrogen has to be bonded to one of those really electronegative atoms. If you don't have a hydrogen bonded to one of those, if the hydrogen's bonded to a carbon or something like that, then it is not a hydrogen bond. Just remember, hydrogen bonds are not bonds, they are attractions. So those are our strongest intermolecular forces. And then we have dipole-dipole attractions. Those are the next strongest. These are for polar molecules. Okay, and again, they're going to be attracted because of that charge separation, right? We get the partial positives and the partial negatives that happen in polar molecules. And then finally, we get dispersion forces. This is in nonpolar molecules. And this is that temporary shift of electrons. Just happens in an instant. There'll be an induced dipole in a nearby molecule, right? And then they go away. And then it happens again, and then it goes away, and it happens again and goes away. These are very weak intermolecular forces, okay? So I do want you to be able to recognize what types of intermolecular forces a molecule would have, and I would expect you to be able to rank them, right? Hydrogen bonds are going to be stronger than dipole-dipole attractions, which are stronger than dispersion forces. And the stronger these forces are, the higher the melting point, the higher the boiling point. So strong intermolecular forces will have high melting points and high boiling points. Okay? Weaker ones will have lower melting points and low boiling points. Okay? So I would expect you to be able to relate that to the intermolecular forces. So here's some examples. Indicate which major type of interactions, whether that's dipole-dipole, hydrogen bond, or dispersion forces, are expected to occur between each of the following molecules. So what I would always do first is draw the Lewis structure, right? Because we need to know, are these molecules polar or nonpolar? So let's try the first one, nitrogen trifluoride. So we, put, we look at our honk rule, Look at our honk rule, and we see nitrogen can make 3 bonds. Fluorine is a halogen, can only make 1. So our nitrogen will go in the middle, and we're going to end up with our fluorines around the outside. And when we do this, right, we need to figure out how many electrons we can have. So we have nitrogen plus 3 fluorines. So we have 5 plus 3 times 7. So we get 26 electrons. We're going to use up 6 making bonds, which means we have 20 left to use. So we go, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 electrons. Now we need to figure out, is this molecule polar or nonpolar? So we look at our electronegativity values. So we will find, actually, hang on. Don't have my electronegativity values pulled up, I'm sorry, but I will in just a moment. All right, there we go. Fluorine has an electronegativity of 4.0, and nitrogen has an electronegativity value of 3.0. So we have a difference here of 1.0. These are definitely polar bonds. So we will draw our dipoles. So remember, we put our partial negatives on the more electronegative atom and our partial positive on the less electronegative atom. And then we are going to draw an arrow for each one of these bonds. So it's always going to go from the positive to the negative. All right, so there's my 3 arrows. So as you can see, 2 of them cancel out, right? 2 of my dipoles are going in exactly opposite directions, the one on the left and the one on the right. They're equal and they are opposite. So these 2 dipoles cancel. But this one doesn't. So we have a leftover dipole. That means that this molecule is polar. Okay, so now we figured that out. So our options, right, we know, right, this is polar, so it will have dipole-dipole interactions. And we always make sure, does it also, sometimes it will also have hydrogen bonding. But we look in this molecule, there's no hydrogens. So it can't have hydrogen bonds, so it's just going to be dipole-dipole interactions. So that's the whole thought process. So if I ask you what type of interactions, you need to go through that whole thing. Let's do another one. Chlorine, Cl2. So chlorine, right, we have 2 chlorines, and they're going to sit side by side. And we have, 2 times 7 electrons to use, so we have 14. 2 of them are going to get used up in that bond, so we have 12 left. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, now we need to figure out, is this molecule polar or nonpolar? Well, they're both chlorines, so neither chlorine is going to pull more on the electrons in that bond than the other, right? Neither chlorine is more electronegative than the other. So this is a nonpolar molecule. And so since it is nonpolar, it has dispersion forces. All right, so that's that. And then our last one, HF, we draw our molecule. So we put H next to F, and then we figure out, how many electrons we have. We have 1 from the hydrogen plus 7 from the fluorine, 8 electrons to use. 2 of them will get used up in the bond. So we have 6 left over. So we go 1, 2, 3, 4, 5, 6, and we're done. Then we figure out, okay, is this molecule polar or nonpolar? So fluorine has an electronegativity of 4.0. Hydrogen is 2.1. This has an electronegativity difference of 1.9. This is super polar, right? Super, super polar. So we put our partial negative on fluorine and our partial positive on hydrogen, and we draw our dipole. So there's no way for that, that dipole to cancel out because it's the only bond in the molecule. So that is for sure going to be a polar molecule. So this one will have dipole-dipole interactions because it's polar, but it has an even more important interaction, right? And this molecule can hydrogen bond because it has hydrogen bonded to a really electronegative atom, right? We see hydrogen is bonded to one of our Fon atoms. And since we have that, this has hydrogen bonding. Since hydrogen bonding is the stronger force than dipole-dipole, if it asks, here it says which major type, we would pick hydrogen bonding. Even though it's polar, hydrogen bonding is a better answer, or you can always put both if you'd like, but you must have hydrogen bonding as part of your answer. If you just put dipole-dipole, I would mark it wrong because hydrogen bonding is also there and it's the stronger force. So those are my example problems. Always make sure to draw the Lewis structure though before you try and figure out what type of bonding there is. So here's the answers. All right, molar mass and boiling point. And so this is for non-polar things. If stuff is polar or if it has hydrogen bonding, it doesn't always follow this trend. It still can, but this is specifically for non-polar things. So things with London dispersion forces. Okay, and our trend is that as your molar mass gets larger and larger and larger, your boiling point gets higher and higher and higher. So, for each one, the one that's kind of italicized, that is your molar mass. And the one that's in bold, that's your boiling point. So you can see that as we go down the periodic table here for the noble gases or for these diatomic halogens, as our molar mass gets bigger and bigger and bigger, the boiling point gets higher and higher and higher. And again, this has to do with the London dispersion forces. Because these molecules down at the bottom have more electrons, not necessarily because they're bigger, but because they have more electrons, they are more polarizable, which means they have a greater ability to shift the electrons one way or another in that molecule. When we were seeing those instantaneous dipoles, right, where the electrons, just happen to be on one side or the other. If it's xenon or iodine down here, they have more electrons, so there's more possibility that you can have a greater charge on the left than the right, or whatever the case may be. So that's why. So we call this. This would be increasing polarizability. And again, this has to do with the fact that they have more electrons. It corresponds to their molar mass, right? As the molar mass gets bigger, but it's because they have more electrons. So more electrons makes larger London dispersion forces, which makes larger melting and boiling points. We see the same thing in hydrocarbons. So these are different, compounds with carbon and hydrogen. And as these, as we go this way, their molar mass is getting larger, and you can see that as their molar mass gets larger, their boiling point gets higher and higher and higher. So again, it's corresponding to stronger London dispersion forces. So go ahead and pause here. We have a little bit more to talk about today, but pause here and do problems 16 through 19 in your lecture worksheet. This will have you work on drawing Lewis structures, and corresponding that to their geometry, figuring out is it polar or non-polar, and what type of intermolecular forces it has. This is a good, bringing together all of chapter 10 to work on these problems. So do those, and then come back. We have one more topic to talk about, heating and cooling curves. Okay, so we've talked a little bit about melting and boiling points today, and so we're going to briefly talk about how intermolecular forces correspond to phase changes. Okay, so this is going to be just like a small topic in chapter 10. But matter will undergo a change of state or phase change when it's converted from one state to another at a constant temperature. So we know, the melting point of water, right, is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius, right? And so at these temperatures, water will, freeze or melt, right? So at the melting point, it can freeze or melt. At the boiling point, it will, boil or it will condense, okay? And then this other one, we're not going to worry about these right now, sublimation and deposition. Sublimation is where it goes directly from a solid to a gas. That's if you bought some solid carbon dioxide, right, dry ice, that sublimes. It goes directly from a solid to a gas phase. And then deposition, you don't really see out in nature, but deposition would be going from a gas to a solid. We're not going to worry so much about those right now. We're going to deal more with melting and freezing and vaporizing and condensing. So going from a solid to a liquid, we know is melting. Going from a liquid to a solid is freezing. Going from a liquid to a gas is vaporizing, right? Also boiling, either one is fine. And going from a gas to a liquid is condensing. And people tend to forget that one. If we went directly from a solid to a gas, like I said, that's sublimation. And that would be like dry ice. And if we are going, it doesn't have the other one. If we are going from a gas to a solid, that is deposition. Okay, so anytime we are going, like on this diagram, if we're going to the right here, if we're going from a solid to a liquid or a liquid to a gas, that is endothermic. And I want you to make a careful note of that. People get that wrong all the time because they're thinking, well, okay, a liquid is at a higher temperature than a solid, right? Which means it's hot, and people get down this line of thinking and they think it's exothermic. It's not. So put that all out of your mind. It's endothermic because the way we got from a solid to a liquid is we had to put in heat, right? We had to cause our, solid to melt. A really good example of this would be like going from a liquid to a gas. Like if you put, you were trying to boil some water to make some pasta, right? You put your water on the stove and then you turn the gas on. You had to put in heat to cause your liquid to turn into, a gas, to boil, to make those little gas bubbles, right? So this is endothermic. Going from a solid to a liquid or a liquid to a gas, those are endothermic processes. Or I guess, from a solid to a gas too, if we happen to ask. So those are endothermic. Going the other way though, going from a gas to a liquid or a liquid to a solid, those are exothermic. And again, people don't think of it as being exothermic because they're like, well, like if I took a liquid water and I wanted to make ice, right? I made it cold. And so people think cold, endothermic, right? Wrong line of thinking. Exothermic, right? Going from a liquid to a solid is exothermic because you had to remove heat. You had to cause heat to leave from your liquid to turn it into a solid, right? So heat is exiting your stuff. It's cooling down, right? Heat is exiting. So that is exothermic. So be really careful. This is something people get wrong all the time. This whether, these phase changes are exothermic or endothermic. So be sure to study up on that. So, melting and freezing, right? Change from a solid to a liquid is at the melting point. Changes from a liquid to a solid at the freezing point. These are the same thing. So, melting points and freezing points are the same thing. They happen at the same temperature. The only reason that we even distinguish it differently is to, figure out, is it heating up or cooling down? But it's always going to be at the same temperature. So that's why it says here, water has a freezing, and then it has in parentheses, melting point of 0 degrees Celsius, because these happen at the same temperature. The solid will melt at 0 degrees Celsius into a liquid, and the liquid will freeze into a solid at 0 degrees Celsius. So these happen at the same temperature. That's why, sometimes you'll see it written as melting point, mostly. So if you see it written as melting point, that's the same thing as the freezing point. Again, it's just denoting, is it heating up or cooling down? And so, similarly, water has a boiling point or condensing point at 100 degrees Celsius. And again, these happen at the same temperature. So it will boil or it will condense, right? Vaporize or condense at 100 degrees Celsius. The only reason that we even talk about it slightly differently is to say, is it heating up or cooling down? Okay. So you're just looking at, is heat being added, right? Is it being, is it going through an endothermic process, right? Are we boiling it? Or is it cooling down? Is it going through an exothermic process and losing heat? So evaporation, so if we were to, look at this, evaporation occurs when water molecules have sufficient energy to escape the liquid surface and enter the gas phase. So the reason it's saying it this way, this escape, is because those water molecules are being held in place by very strong hydrogen bonds, right? Water molecules look like this. And water molecules fall into our FON category, right? It can have hydrogen bonding, and so there's this attraction here between the hydrogen and the oxygen that is a really, really strong attraction. And so that is why water is a liquid at room temperature, where, even though it has a really, really low molar mass, right? It only has a molar mass of 18.02. And so it should be, like a gas based on that. But since it has hydrogen bonding, that strong interaction, it's able to hold those other water molecules in place. And it has, it will stay as a liquid. But when we input enough heat, right, using this Bunsen burner, if we input enough heat, we can break this attraction that's holding these water molecules in place. And when they have enough energy to break that attraction, then they can evaporate and go into the gas phase. So that's why it's phrased like that. So we need to input enough energy to overcome those attractive forces and allow that gas molecule to escape. Same thing kind of happens at the melting point, right? We need to put in enough energy to break the attractions that are holding the solid together and turn it into a liquid. So at the boiling point, though, still on the liquid and gas, the molecules have enough energy, they can overcome those attractive forces, and they can finally go into the gas phase. And again, for water, this would happen at 100 degrees Celsius. Sublimation and deposition, like I said, they're kind of unusual. Sublimation is when we go directly from a solid to a gas. Your example for this one, like I said, is dry ice, solid carbon dioxide to a gas. The reverse process is called deposition. You won't ever, really see that out in nature, and so I'm not going to give you an example there. I've actually only seen it once in a reaction that I've done, but it's the opposite, so going from a gas to a solid. And here's your example, right? For example, dry ice, which is solid carbon dioxide, sublimes at negative 78 degrees Celsius. And we call it dry because it doesn't form a liquid as it warms, right? Whereas regular ice, right, will form a liquid at room temperature. So we have these heating and cooling curves for water. Okay, so I want you to pay careful attention to this. I'm going to have you draw the shapes of these. So I want you to know kind of what's happening at the different shapes. My big hint to you is that sloped lines are phases and flat lines are phase changes. Okay. And so let's think about some ice. We have ice at negative 25 degrees Celsius. Since this is below, right, our big temperatures for water are going to be 0 and 100. That is when the phase changes for water happen. Since it's below 0, right, negative 25 is below 0, that means that our ice is in the solid phase. And it will stay as a solid until it hits 0 degrees Celsius. And when it hits 0 degrees Celsius, it warms up enough to get to 0, then it will start to melt. And when it starts to melt, right, let's back up. So 25, we heat it up until we hit 0. And then you'll see the graph flattens out. And the graph flattens out because the energy is no longer being used to kind of warm up the molecules. Instead, that energy is being used to break the intermolecular forces. Okay, so that's why we see this flat line in the graphs for the heating curves. And the flat lines will always happen, like I said, at phase changes. So the curve will stay completely flat until all of the ice is melted. It will stay at 0 degrees Celsius until all of that ice has melted, turned into water. And as soon as it's all done melting, then your water will start to heat up. And it will go from 0 and it will go all the way up to 100 until it hits 100, right? And then again, that energy that you're putting in, instead of being used to like warm up the water, now it's going to be used to break the intermolecular forces between the water molecules. And so it's going to break those intermolecular forces and allow the water to be turned into a gas. Okay, and so that takes a lot of energy. That's why that line is so long there. but it's going to stay at 100 degrees Celsius until all of the water is turned into a gas. So you'll notice, like if you boil water, you can do this at home actually while you're, making pasta, right? If you were to boil some water and you took the temperature, you're boiling water, even though you're inputting heat, the temperature will never go above 100 degrees Celsius. And that's because of this, right? If we keep putting in energy, that energy is being used to break the intermolecular forces, to evaporate your water molecules. It's not being used to heat up your water. Your water will stay at or right around 100 until all of the water molecules has been converted into steam or vapor. And once we've converted it all into steam or vapor, then it will go back to heating up and getting warmer. Okay, so this is how heating curves will always look. But like I said, the key, they are sloped lines for phases, flat lines for phase changes. Very, very important. So all of the changes of state during the heating of a solid can be illustrated using a heating curve. Heating curves are graphs. They have temperature on the vertical axis. So temperature will always go on this side. And on the bottom, this will always be like heat added or something like that. Okay, and again, changes of state. So phase changes are horizontal lines. They are flat lines. Change in temperature, right, during the phases will be a sloped line. So keep that in mind. Sloped line equals phases. Flat lines equals phase changes. Okay. So here's another heating curve for water. It's just another way of depicting it. Again, this one starts at -40. And if it's at -40, right, because our big temperatures for water are 0 and 100. So if it starts at -40, it will heat up until it gets to 0. And once it gets to 0, then your solid will start to melt. And it will stay at 0 till all of your solid has melted and turned into liquid. And then as soon as it's all melted, then it will start heating back up again. And it will heat up until it gets to the boiling point, right? It will heat up until it gets to 100. When it gets to 100, your water will start to boil. And it will stay at 100 till all of that water has turned into a gas. And once it is all turned into a gas, there's no more liquid water left, then it's able to heat back up again. Okay, so I want you to be able to recognize, on this heating curve, whether something would be a phase or a phase change, right? Is that line sloped or flat? And I would also want you to be able to recognize which phase change is happening. Is it melting or is it boiling? Or is it, a solid or is it a liquid, right? What is happening in these different portions of the graph? So here's another way of looking at it. Okay, so again, starting at -20, we'll heat up until it gets to 0, and then it will melt, right? And once it's all melted, it will start heating up again till it gets to 100. Once it hits 100, it will stay flat, right? It will all boil, and once it's all boiled and changed into steam, then it will continue heating up again. During these phase changes, so the only thing that's really new on this particular slide, during these phase changes, you have two phases present. Okay, so we started with ice and we heated it up to 0, and once it starts to melt, right? Think about melting ice, right? Until it's all melted, until it's here, right? Anywhere in between, you have both solid and liquid because, not all of it has melted yet. Some of it's melted, but not all of it. So we have solid and liquid present during the phase change. Similarly, during this, this boiling phase up here, this vaporizing, we have water and steam, or liquid and gas while it's boiling. And again, you can think about boiling some pasta, right? When you're boiling water, you have liquid and gas bubbles that are being formed until, it all boils. If you left that pot on the stove, for quite a while, you would evaporate eventually all of that water. And then, you could heat up your steam. Wouldn't be very good for your pot probably, but you could do it. And so the last bit today is a cooling curve. You can also draw the exact opposite, but the same thing is also true. Sloped lines, right, are phases. Flat lines are phase changes, so those are still true, okay? The only thing that's different is that now your graph is going down instead of going up because it's a cooling curve. Heat is being removed over time. So over time, your temperature is getting lower and lower and lower. So we're going to start off really hot. Here it starts off at 140, and it's steam until it cools down to 100. Again, we still have these big temperatures for water, 0 and 100. And it will cool down until it gets to 100, and then it will cause condensation. Your steam will turn into a liquid, and once all of your steam has turned into a liquid, then it will start cooling down again. And then it will cool all the way down to 0, right? And once it gets to 0, then your water will start to freeze into ice, right? You can put your water, say you boiled some water, you made some hot water, you stuck it in the fridge, right? It would cool down, but it wouldn't change phase until it gets to 0. Once it gets to 0, it would start to freeze into ice, and it will stay at 0 until it is all frozen. And once it's all frozen, then it will keep cooling down. So this is a cooling curve. So it's different from a heating curve, right? Heating curves go up, cooling curves go down. But otherwise, it's got all of the same things, but we are going to have different labels for our phase changes, right? This is condensing and freezing instead of, melting and evaporating, right? So just make sure you know which labels go with which types of curves, and you can recognize the different phases and phase changes. So now you need to get some practice on this and do problems 20 to 25 on your lecture worksheet.